Okay, you're here to learn about Hooke's law and elasticity of materials. So I have three identical springs hanging from a rod, and they hang down the same length. They're identical. And so now I'm going to add two different masses to two of the springs. So on the middle spring I put a 1 kilogram mass, and on the spring on the right I put a 2 kilogram mass. And so predict to the best of your ability what's going to happen, and try and predict exactly what's going to happen. So probably you correctly guessed that the string is going to stretch a certain amount, and how much it stretches, 1 centimeter, 4 centimeters, 10 centimeters, depends on what? It depends on the thickness and the material that the spring is made out of. So some springs are stiff and some springs are loose. So let's say this one stretched 4 centimeters. Then you should have guessed that the identical spring with twice the mass, which means twice the force, right? The stretching force here is 1 times 9.8, or 9.8 newtons. The stretching force here is double, or 19.6 newtons, right? The stretching force is mg. And so it stretched it twice as much. And so the stretch for most springs, as long as you don't stretch them too far, the stretch will be directly proportional to the force you applied. And the equation that describes that is Hooke's law. Since I have this diagram from the internet, I'll show you. Right? This is just what we described. And since I put it here, I might as well use it. Okay, that's what I drew. And it shows the stretch of the spring measured to the bottom of the mass hanger. Okay? So anyway, if we did a graph, so here's the graph of what we just did. A force of 1 kilogram, which is 9.8 newtons, I'm just calling it 10, gives a stretch of 4 centimeters, and a force of 2 kilograms, or approximately 20 newtons, stretches the thing 8. And so we might predict that if we triple the force, we're going to get triple the length of stretch, and quadruple the force, and we get quadruple the length, and we get a straight line, where 0 force means 0 stretching. And so the amount that it stretches for force is a constant. The slope of this line is a constant, and so the equation for this is Hooke's law. The force equals, there's a negative sign there that I'll explain in a minute, the constant times the stretching distance. So the slope of this line, right, is the k. It's the delta y, the change in force, over the change in length, or the force we applied over the amount it stretched. And notice that whether we do 10 newtons divided by 4 centimeters, or 20 newtons divided by 8 centimeters, or 30 newtons divided by 12 centimeters, in every case we get 2.5 newtons per centimeter. And this is what we call the spring constant, or the spring force constant for this spring. Let's practice on one more example. So in this case we're given K, right? The 20 newtons per meter. It's in newtons per meter rather than centimeters in this case. We can use either units or Fine, so this is the K for the spring, and it's constant. And we're given how much it's stretched. So find out what the pulling force is. Use Hooke's law to calculate that. So pause the video and do the calculation. So see if you got this. So I wrote down Hooke's law. We always start the solution with an equation. So the force equals minus K delta X. I'll show you what this minus sign is here for in a minute. So I put down minus 20 newtons per meter, that's given. And the amount of stretch is 25 centimeters, but the units aren't going to cancel, right? If I put this in centimeters, my answer is going to be Newton centimeters over meters. So that's a key that we got to convert the 25 centimeters to 0.25 meters. The meters will cancel, and I get a negative 5 newtons per meter. Why is it negative? Because Hooke's law is actually used to calculate the spring force, not the applied force. So notice the displacement is positive, but the spring force is in the opposite direction. The pulling force, so if the question is how much do I have to pull it, in that case we don't want the minus sign. So that's what the negative is in Hooke's law. And depending on what you're asked, you want to use that negative or not. So that ends my introduction to Hooke's law, but if you want to go on to study elasticity and Young's modulus, I'm going to show you how Hooke's law connects with the concept of elasticity and Young's modulus of materials. Okay, do this thought experiment. So I'm taking 4 of these springs that are 20 newtons per meter, the one we just observed in this diagram, and I'm taking 2 of them and linking them end to end together. So this is called series. These are connected in series. And now I'm going to stretch the 2 springs by the same 5 Newton force that I used back here that we calculated. Then I'm going to take 2 more, 4 altogether, and attach them to a place that can't move, and then connect them with a bar. And then now we have 2 springs in parallel. And I'm going to pull on these 2 springs in parallel with the same 5 Newton force. Okay, so do that thought experiment in your head and see if you can predict how much this 2 springs in series is going to stretch and the 2 springs in parallel is going to stretch. Go ahead, pause the video and give that some thought and commit yourself to an answer. Okay, let's see how good your intuition is. So when I apply a force of 5 newtons here, both springs, that's the tension throughout both springs experience a 5 Newton force when they're in series. And so this will stretch 25 centimeters, and this will stretch 25 centimeters, and so this will stretch twice as far. It'll stretch 50 centimeters. Whereas when I apply a force of 5 newtons here, both springs are pulling back on that bar. And so my applied force is only 2.5 newtons to each spring. And so the spring is this, in this case, the stretch is only going to be half of the 25, or 12.5 centimeters, whereas this delta x is 50 centimeters. So the spring constant depends on 3 things. It depends on the length of the spring. It depends on the thickness of the spring. So this is like actually what we're doing. Let me just pause for a minute. We're going to, when we do elasticity, we apply it, say, to a wire. And we're going to apply a force to a wire and see how much it stretches. or compress it and see how much it compresses. So how much it stretches, the delta x, or in this case the delta L, is going to be a function of the length, the original length of the thing. So if the thing is longer, it'll stretch more. However, it will also be a function of the thickness. So if the wire that I'm stretching is thicker, the same force is going to stretch it less. That's the idea in the two parallel springs. And so if I take a wire and I double its diameter or radius, I actually quadruple, right? The cross-sectional area of the wire is going to be pi r squared. So if I double the thickness, I'm going to have 4 times. It would be like 4 springs. And so the amount that our wire over here, or rod, or whatever it is, the amount it's going to stretch, the delta L that we get, is going to be proportional to the force we apply, right? Double the force, double the stretch. It's going to be proportional to the length of the wire, double the length, double the stretch, and inversely proportional to the number of springs, or the cross-sectional area of the thing we're stretching. So what's the last thing that it's going to depend on? The last thing that it's going to depend on is the material that it's made of. So if it's made of rubber, it's going to be easier to stretch than if it's made of steel. And so that's Young's modulus. That's the characteristic or ability of something to stretch or not stretch. And the units of Young's modulus are force per unit area. And so Young's modulus goes into the equation in the denominator. And you'll see that the units of force per unit area and the inverse units of Young's modulus cancel each other out. And so these are the 3 factors that determine how much stretch we're going to get in any case. And Young's modulus is the characterization of any material independent of its length or its area, because we've included those in the equation.